So we're working on indefinite integrals, and all our examples went to infinity, but this one doesn't. You know, well, why would this be? I said indefinite integrals. Yeah, improper integrals would be better. Why is this an improper integral? Because, I mean, my limits don't go to infinity.
Because sine of pi over 2 is 0.
Yeah, close. Sine of 0 is 0.
Oh.
Yeah, no, but you had the right idea. So thank you so much. Yeah, this is undefined at the end point of the limit. So here's what we'll do. We'll rewrite this as the limit as b approaches 0 of the integral from b to pi over 2 of cosine of theta over the square root of sine of theta d theta. Nice. And let's just take a quick look at this, graphically speaking. Because remember, this refers to the area between this function and the x-axis in the limits of 0 to pi over 2. So, okay, let's take a quick look here. Shut this one off. And let's see, this one right here, 0 to pi over 2. So let's kind of zoom out a little bit this way and then zoom down a little bit. Now I'll never be able to see the top of this function, but you can see that this graph approaches the y-axis pretty quickly. I mean, after you get above a height of like 3 or 4, there's not much area there. So that tells me that there's probably some hope that the area that is bound up between these two or three curves, or the curve and the two axes, is probably finite. So let's check it out. We'll check it out by calculating that. Yeah, let's see. I wanted to get the pi over 2 in here for us, show up, but it's not cooperating. Yeah, whatever. Let's get back to the actual work here. Now, I put in my lower limit of b, but I need to find an antiderivative here. Well, the good news is that I don't need to do anything really fancy. I can just get by with the u substitution. Now, there's two possibilities. You could let u equal cosine of theta, and du be a sine of theta and a d theta, or the other way around. Let u equal sine of theta, and du is going to have a cosine of theta d theta. Which way do you think works? Which way do you think we're going to use?
I think sine of theta sounds good.
Yes, sine of theta, because the du is going to be right here, cosine of theta d theta. Whereas if you did it the other way around, and you're looking for a sine of theta d theta, you're not really going to find it because that sine of theta is in the denominator. It's not next to the d theta like we have with the cosine of theta. So, all right, good suggestion. We're going to let u equal sine of theta. Du equals cosine of theta d theta. Well, that's pretty special because cosine of theta d theta, hey, that's right there. So we're good in that sense. Well, the question becomes, do I want to change the limits of integration? I guess I can if I want. Let's just change them in this case. So I'll do u of pi over 2. Well, that's going to be sine of pi over 2, which is 1. And now my lower limit, u of b. Well, that's just going to be sine of b. Okay, we're stuck with that. Let's rewrite my limit now. That's going to be the limit as b approaches 0 of the integral between sine of b and 1 That's my du term over the square root of u. Looking a lot simpler, although not as friendly as I want just yet. So let me rewrite the integrand as u to the negative 1/2 du. And that looks a little bit more workable. I think I can find the antiderivative of that one. So some help on that. What's the antiderivative of u to the negative 1/2?
Two u to the 1/2.
Beautiful. 2u to the 1/2.
Shouldn't it be -2?
Good question. Let's check it by differentiating. 1/2 times 2 is 1. Subtract 1 from the exponent would leave me u to the negative 1/2.
Oh, wait, I see. Okay.
So I think that works. But I appreciate you checking me though. Limit as b approaches 0 of 2 times, well, that's really the square root. So it'd be, 1 to the 1/2 minus square root. And I've left the 2 out in front here. Square root of the sine of b. So that's looking okay. Can anyone tell me what's going to happen with this limit? Actually, I don't need the limit there anymore. What's that limit going to equal?
Zero.
Yeah. As b approaches 0, sine of b is going to approach sine of 0, which is 0. Square root of 0 is 0.
Can I ask you a question?
Yes, please.
Is that true with any trig functions inside of
Inside of a
limit?
radical?
Yes.
Yeah. So, and I apologize I didn't really show it, but really what I was doing here is, because this is a continuous function near this point, and actually sine is continuous everywhere, I was really looking at the square root of the limit as b approaches 0 of the sine of b, which became sine of 0. And sine of 0 was 0. So that's what you're doing, is you're using some of our work from Calc 1 with limits of continuous functions to interchange these things and take that limit inside the radical like that. Does that help out?
Thank you.
Mm-hmm. All right. So kind of like what we expected. We expected that, the area here does look like it would be finite, that this curve gets pretty close to the y-axis really fast, and that much above, say, 4 or 5 or 6, there's really not much area. Even if you go all the way up to infinity, there's just not that much area there. So that's probably finite. And what you would say here, if WebAssign happens to ask you, does this integral converge or diverge? It converges. And then they'll probably ask you to calculate it. It's going to calculate to 2. Okay. Anything else on this one?
I have a question.
Yeah, please.
So why did we, I don't know if it's just the way we're doing the problems, but it was because wouldn't the answer have been the same if you didn't even make the beginning 0 a b and then limit b approaches 0? Or is that just the way we're doing the problems right now?
Well, this is an improper integral as it stands because the integrand is undefined at 0. So the way around that is to take the limit here. If you go back to Calc 1, these functions have to be defined, these functions have to be defined and continuous in this interval, or at least have a finite amount of, like jump discontinuities. That's not true here. This is not a continuous function at 0. So really, we shouldn't be actually doing this. And our work around this is by taking the limits.
Oh, my bad.
Now,
I see.
there are some problems, and maybe even this is one of them, that you could get around, or you get the right answer without plugging in this limit stuff and doing this limit stuff. But at the very, very least, you're going to make your instructor unhappy. And probably more accurately, you're probably going to lose some points if you don't use limits here. So it is something I want to see, and I appreciate the question because it gives me another chance to remind you that I do want to see the limits here. There are some problems that I can write that if you didn't write the limits and you just tried to plug it in without the limits, you'd get an answer, but that answer would be wrong. I don't know as though I need to try and trick people like that. I just ask quite simply that you remember the limits, all right? Because I don't want to try and trick anyone. But there are problems where if you don't use the limits properly, you're gonna end up with the wrong answer. All right, so good question. Anything else on this one before I move on? Okay. Kind of another one along the same lines like that. And if you'd like, I can let you work on this one. No, let me get a different sheet of paper here. The integral from, let's see, 0 to 5 of dx over the cube root of 5 minus x. So, like, what's the problem here?
The 5.
Yeah, the 5. The denominator is undefined at the 5. So you should start out by taking the limit as b approaches 5 of the integral from 0 to b dx over the cube root of 5 minus x. All right, do you want to work on this one or do you want me to do it? It's up to you. Okay, let's see you work on it. So the first thing I would do is I'd rewrite this using rational exponents. So 5 minus x to the negative 1/3. And then, when du equals dx with your substitutions, you can kind of integrate these by thinking. But if you let u equal 5 minus x, du doesn't quite equal dx. It's a little negative sign that we got to deal with. So dx equals negative du. I'm also going to change my limits of integration. So at 0, if I plug in a 0 here, u of 0 is going to give me 5. Well, 5 minus 0, which is still 5. And then u of b is going to give me 5 minus b. So let's plug in both of those along with our substitution and get this as the limit as b approaches 5 of the integral from 5 to 5 minus b of u to the negative 1/3 times negative du Yeah, let's make that look like a negative 1/3, not a something, whatever that would be. Okay, this is nice because we can integrate this. So let's do that. Add 1 to the exponent, divide by the same exponent. Sometimes people try and do too much at one step, and then they make mistakes. So you can just write u to the 2/3 divided by 2/3. There you go. So you've added 1 to the exponent, divide by the same exponent. And then maybe in the next step, again, not trying to do too many things at once. In the next step, I can invert and multiply. So limit as b approaches 5 of
Shouldn't
3/2.
Negative, shouldn't it be a negative?
Yeah, there's a negative here someplace.
Negative
I'll
u.
just put that there.
Yeah.
Negative 3/2 u to the 2/3. Thank you. Between 5 and 5 minus b. This negative 3/2, let me take that out front. Negative 3/2 times the limit as b approaches 5. And let's put in our terms here. 5 minus b to the 2/3 minus 5 to the 2/3. And like I said, I took the constant out in front. As b approaches 5, what happens to this term?
Goes to 0. Disappear.
Yeah, disappears, goes 0, right? So that's a big goose egg there. And I'm left with negative 3/2 times negative 5 to the 2/3. And the two negatives cancel, so it gives me a positive 3 times 5 to the 2/3 over 2.
Nice, that's what I got.
Yay, great minds think alike, right? Of course, the flip side is fools seldom differ, but that doesn't apply here. Awesome. How are we
I
looking
have
with that
a
one?
quick question.
Please.
It was, I guess I was a little confused on how it was a negative dx when we did the u substitution. I was kind of a little confused how we got the negative dx.
Sure. So when you differentiate this, derivative of 5 is 0, derivative of x is negative 1. So,
Okay, and then you just, okay.
and then, yeah, so technically what's going on here is that you have du by dx equals negative 1. And then you multiply both sides by dx, and that's what gives you this one down here, is du equals negative dx, when you multiply both sides to clear out the fraction. So you multiply by dx there.
All right, thank you. I appreciate that.
No, thank you. I appreciate the questions. I really do. Anything else I can help out with on this one?
I did something wrong. Back when you had u to the negative 1/3, I didn't make it negative 1/3. I left it underneath and had it as u to the 1/3.
That's okay, but you can't integrate it from there.
You can't. I try to do like the ln. Why doesn't that work for that?
ln is be 1 over u, not 1 over u to the 1/3.
Okay.
So the ln only works when you have 1 over u, not 1 over u to any other power. It has to be specifically u to the first power in the denominator. Good there?
Yep.
All right, thanks for asking. I see that a lot. A lot of times people, anytime something ends up in the denominator, there's a gut reaction to say, oh, that's the log. Only if the power is 1. So in general, if you have 1 over u to u, that's when you have the natural log. Okay. So from my students from last semester, did you guys like that houseboat joke that we told? Is it worth retelling here? A couple of you, Jackson, Marissa, Maya. No comments?
You can go ahead
All
and
right.
tell it. I don't remember it off the top of my head that clearly.
You don't? All right, all right. So
You didn't mention the winter.
yeah. I did?
I don't think you mentioned the winter.
All right.
And
Well, shame on me if I didn't. So it's time to learn how to make a houseboat with calculus. So here you go. We're going to integrate the function 1 over cabin d cabin. So there. Now, this is exactly the form that I was talking about just a second ago. You know, this is to the first power. So when you integrate that, it's the natural log. So it's the natural log of cabin. But there's one thing that I always have to remind my students of. When you find an indefinite integral, what else do I need? Come on, what's missing here?
Constant.
Plus your constant. Now let's look at what we just built. This is a natural log, or better yet, just the log. So we've got a log cabin plus the C, log cabin on the C. That's your houseboat. Yay. So go ahead and amaze your friends. I know you guys are all muted, otherwise I'd hear roars of laughter. So I'll just thank you in advance.
I haven't had it wrote down my notes like 6 years ago.
Yeah, that was it. There's just
so
nothing. Do you still find it funny?
Yeah, can't believe I wrote that down.
All right, so let's see here. Well, let's kind of stick with this theme for just a little bit here. This log stuff, and remind you that when we have 1 over something like this, you end up with a log. Let's look at this example. Let's see. The integral from 1 to infinity of 1 over x dx. So, okay, what's going to go on with that one? Well, first we'll start out like we always do with the limit as b approaches infinity of the integral of 1 to b of 1 over x dx. Okay. You should be pretty good at this by now. What's the antiderivative here?
An x.
Ln of x. Good. So ln of, I should probably put the absolute value. We don't really need the absolute value because the values of x we're going to be putting in here are already positive because we're going from 1 to eventually infinity. But I'll just put it there anyways. So, okay. That's the limit as b approaches infinity of the ln of b minus the ln of 1. Now, the good news for us again is that ln of 1 is 0. Well, what's going to happen as b approaches infinity of the natural log of b? What's that limit going to go to?
Infinity?
Infinity. You're not going to get a finite value. So, therefore, this integral, 1 to infinity, 1 over x dx, diverges. It's not finite. There's an infinite amount of area there between this curve and the x-axis. It doesn't really look like it too much, but there is. So, wow. And actually, you can generalize these things. So let me give you a couple general statements about stuff like this. Let's do this here. So in general, integral from 1 to infinity, and it doesn't exactly matter where you start, as long as the upper one is infinity, of dx over x to the p is convergent if p is greater than or equal to, or no, p is strictly greater than 1, not equal to. We just dealt with the equal to case. If p is equal to 1, it diverges. That's what we just showed above. So it's convergent if p is greater than 1, is divergent if p is less than or equal to 1. So it's a nice little tidbit to keep around. These are called p-series. We'll see more of those when we deal with Taylor series in chapter 10. Is it 9 or 10? I think it might be at the end of 9. In any case, so a couple nice little tidbits there. Now, we can look at a different type of integral. So, well, the same integral, except different limits. So, if everyone got this, can I move on to the next page here? I'll just move it up like that a little bit. Let's stick with the same integrand, but different limits. And this time we're going to look at the integral from 0 to 1 of 1 over x to the p dx. Now, why would this be an improper integral? What's wrong here?
P of 0 is independent.
Yeah. At 0, the denominator is 0, so it's undefined. So that's kind of a bad thing. So, all right. This one is convergent. This time it's if p is less than 1. So if p is less than 1, it's going to converge. If it's divergent, if p is greater than or equal to 1. So the value of p here again is going to tell you if it converges or diverges. I'm going to again take this back to the graph and look at the areas involved and try and give you a little intuition as to why this is happening. So let me go here and down to here. Turn this one on and make it a little bit more, a little bit bigger. All right, so right now I have p is 0.4, and for values of p that are less than 1, you're going to have it converge. What does that mean about the area here? What's that telling you about the area underneath this curve and between the axes?
It's finite.
It's finite. Good, it's finite. So let's get rid of that. We'll make that 0.5. There we go. But watch what happens to this as I increase the values of p. The area, what's happening to the area, would you guess? It's getting bigger, yeah. And at p equal 1, that's your break-even point. At this point, there's now an infinite amount of area above here. And you can see what happens as values of p get even bigger. As values of p get even bigger, you just got more and more area, in some sense, maybe. I mean, we already knew there's an infinite amount of area there, and it's just getting bigger. There's a mathematician by the name of George Cantor that did a lot of work with infinity, and there's really a couple different kinds of infinity, but that goes well beyond this class here. In any case, so coming back over to here, for values of p that are less than 0, you can see that, oh yeah, that's pretty nice. That's a pretty slender looking sliver of area that goes up towards positive infinity here. So you can well believe that that would be a finite area as opposed to something over here, which looks more like an infinite area, which is what it is. All right, let's do one last one here from this section. And you know what, before we get to the actual, now let me write down the problem here. So the integral from 0 to infinity of sine of theta e to the cosine of theta d theta. So that's our integral. And it's an improper integral. And working with it, we should really start by saying, all right, we'll take a limit as b approaches, which point of this, which part of this was the improper part?
Infinity on the.
Yeah, thanks, infinity. So 0 to b of the sine of theta e to the cosine of theta d theta. Well, let's try and look at this and see what we can see. So let me shut this one off. Go up to here. And this one's kind of interesting. So let me turn on the graph here. And part of this graph lies above the x-axis. And let's see if we make this a little bit bigger. No, other way around. There we go. And you can see it starts to repeat itself. And there's another one. But here's the interesting part. There's a part that lies below the x-axis as well. Now, one of the things you should start to expect to see when things converge is that those areas between the curve and the x-axis start to get, well, not just the x-axis, could be the y-axis, but the area between the curve and the axis start to get really small pretty quickly. Is that happening here? Are those areas and those little orange and purple humps getting closer and closer to 0? Doesn't look like it to me. In fact, if you take a look here, can anyone tell me what this integral is giving me?
2.35.
Right? And the interpretation is it's just the integral between 0, 0 and this point. In fact, the origin up to here. So I should probably put in another point here. Let's do that. 0, 0. There we go. So the integral of the area between those 2 points. And I look at the integral for the area between the next 2 points, between pi and 2 pi, and guess what? They're the same except for one important feature. What is that one important feature?
Negative.
It's negative. So you got a positive area and a negative area, positive area, negative area. Well, what's going to happen if you try and find the area going all the way out to infinity? Are you going to get anything? Positive, negative, negative, you know.
Wouldn't it just be 0?
Maybe, maybe not. Don't know. We're going to have to look. But it's certainly not as nice as some of these other ones. Some of the other ones where, I mean, it just went to 0 really, really quickly. You're pretty confident that, okay, that's getting close enough to the x-axis, fast enough. So we'll take a look back at what in the book is problem 17. This is getting really close to the x-axis fast, so yeah, I'm pretty sure that's a finite area. We're not seeing that with this. This one's just a big mess. So what happens when we integrate? Let's find out. Here we go. Well, I guess the first hurdle in integrating is we're going to need a substitution, because I don't know an antiderivative for this. I'm certainly not going to do this with integration by parts. How would you work this? What should you do?
U equals cosine theta.
Yeah, perfect. It's like U equal cosine of theta. And there's a little confusion on this in the last step, so let me just show it to you. Just occasionally, maybe it's not a bad idea. If I differentiate both sides with respect to x, or actually with respect to theta, I should say, I get du by d theta is minus sine of theta. And then multiply both sides by d theta, du equals minus sine of theta, d theta. Usually I don't bother to show that middle step, and you don't have to either. But let's do something else here. Let's change our limits of integration. So I want u of 0 and u of b. So it's going to be the cosine of 0. What's the cosine of 0?
1.
Thank you. And then cosine of b. Let's plug all that stuff in and get our new integral. So it's going to be a limit as b approaches infinity of the integral from 1 to cosine of b of e to the u times minus du. We need to get rid of that minus sign. I forgot to do that. Because we got sine of theta, d theta. I got to put that negative sign to the other side. So minus du. Okay. Let's not lose the negative sign this time. That's going to be the limit as b approaches infinity of negative e to the u between 1 and cosine of b. Okay. So I'll take that negative out in front, negative the limit as b approaches infinity of e to the cosine of b minus e to the first power. And here's where we run into a problem. Here we're okay, right here. What happens as b approaches infinity of e to the cosine of b? It's just going to be a weird up and down function. It's not going to settle into anything. So this limit does not exist. And overall, what that's saying is that this integral diverges. So therefore, the integral 0 to infinity sine of theta e to the cosine of theta d theta diverges. This doesn't converge. And it's not surprising, given what the graph looked like. that we got some kind of a weird result like this. Just doesn't converge to any finite value. So,
So if,
all right, there was 2 questions there, one at a time.
How
right.
do you know it doesn't exist?
sorry, God. Okay, you go.
All right, ladies first.
How do you know that it doesn't exist? Is it just because it's a weird like number?
Well, in order for this limit to exist, e to the something would have to kind of peter out to a value. Now let me see if I can't show you something with decimals here. If I had y equals e to the negative e raised to the negative px, you can see that for various values of p here, this graph, decays. It gets really close to the x-axis, and depending on the value of p, it does it so faster or slower. But if I had in e to the cosine of x, then the graph doesn't ever settle down to anything, does it? I mean, it just goes up and down and up and down, and that's it.
So you're graphing to figure that out, kind of?
Yeah, the graph helps. Yeah, sure. Because when you're looking for something to converge, let's see, y equals, let's do 2 minus, I don't know, 1 over e to the x. Eventually, what you're expecting to see is a graph is going to settle down to one number, kind of like this. Eventually, it gets closer and closer to 2. That's what's going to go on. But our graph here doesn't get closer and closer to any number. It just keeps on going up and down and up and down. It never, settles down on one specific number. So there's no limit there. Yeah, I think the graph in this one is particularly helpful. So that is kind of nice that we can see it so clearly on Desmos and our graphing calculators. All right. There was 2 questions. That was the first one. Who else had one?
Me. So what does an answer to one of these look like? Do we just say like diverges, like on web work particularly?
Yeah.
Because don't get an answer.
They're going to ask you if it converges or diverges. And if it converges, they're going to want you to calculate a number. If it diverges, then that's it. There's no number that you can give it. So you just say diverges.
Right, okay.
All right, awesome. All right, let's take another break. We'll see you in a few minutes.